Okay, discrete math, period 5. Woo woo, second try. Blah 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 blah. Here's what's going on. We are learning about graph theory and polyhedra. We are going to finish learning new topics this week, and then we'll have a big graph theory test next week on some kind of days, unclear. So the first thing we're going to do really quick is go over the homework. This was homework that was due last Friday, and I meant to send a message over the weekend reminding you to do it by Monday if you hadn't already, but I did last night post that you should do this homework. John, did you do it?
No.
All right, good. All right, so you had two chances plus to do this homework. Let's do it right now. I'm gonna go really fast through this because we accidentally did most of this problem last week. Remember?
Yeah.
Yeah.
And then you were like, oh.
And then I was like, oops. Yep. So the number one is an extended theorem, and we need this theorem pretty badly. So I want to care about this theorem. So here it is, theorem. If G is a connected, simple, planar graph. All right. With epsilon edges. Stop doing that, Hayden. And n greater than or equal to 3 vertices. Then, put the then here. Epsilon is less than or equal to 3n minus 6, yeah?
Yeah.
Okay, and Gossett walks us through a proof of this, most of which we did in class together. So just very quickly, but I didn't do this in 9th period. Anyway, whatever. First I define the degree of a region. The degree of a region is the number of bounding edges of that region. And an edge terminating in a degree 1 vertex is to be counted twice. So recall, if the situation is like this, then the degree of this region is 2, and the outside is also a region which has degree 2, yeah? Okay, and then let's see, you have some other situation then the degree of this region is 3 because the number of bounding edges is 3, but the degree of the outside region is 5, yeah, because there's 5 doors in and out of the region or whatever, or just you need this to happen so that all the things work out. All right, and then part A asked just some thinking questions. What is the degree of a region inside a loop? Answer. Actually, I have no idea what the answer to that is. I guess 1, but I could also be talking to 2. I kind of don't care because I only care about this if it's a simple graph, but I guess 1. I guess just 1.
It's 1 because if you just consider a vertex with a loop, there's 1 and 1. There's 2 regions, they both have degree 1.
Is that, you agree? Dylan agrees. I'm going to hold off on that. Okay, good. Hold off on agreeing. What is the degree of a region between 2 edges that have the same pair of vertices at their ends? Just 2. Yeah. Okay, good. So then we get to the real questions. B. What is the lower bound of the degree of the regions in a connected, planar, simple graph with n greater than or equal to 3? Well, if it is connected, planar, and simple, and n is greater than or equal to 3, well, you can't have just 1 vertex, because that would not be n greater than or equal to 3. You can't have just 2, so you have to have 3, and if it's simple, they can't connect back up. So this is pretty much the smallest possible graph, which is connected, planar, and simple with n greater than or equal to 3. What is the degree of this region? 4, correct. So can we go lower than 4? We can, by making a triangle. So I claim that the degree of a region is minimum 3, because it just can't be 2 if the graph is simple. Follow? That was a little bit of a crappy argument, but I think we did this already. Okay, good. So the minimum degree of a region is 3 if the graph is connected, planar, and simple. Okay, part C said prove that the number of degrees of the region is twice the number of edges. Well, just duh, right? Given any region, la 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 la. then if you count all, let's like actually do this properly. So maybe something like this. So if I was going to count all the edges by counting the degrees of all the regions, then I would be like, this has degree 4, this has degree 4, this has degree 3, and the outside has degree 1, 2, 3, 4, 5. But then I've double counted every edge, right? Say right. All right, it's a riveting video. So the sums of the degrees of all the regions in a simple planar connected graph is twice the number of edges. Wonderful, wonderful, wonderful. Part D says, combine parts B and C to show that if there are row regions, then rho is less than or equal to 2ε/3. Well, if the minimum degree of a region is 3, and the sums of the degrees of all the regions is 2ε, then it must be true that the sums of the degrees of all the regions has to be less than or equal to 2/3 epsilon. Did I do that right? No. What? Hold on. The sum, then these could all be 3. So less than or equal to 3 epsilon.
3 rho.
3 rho. Yes, because that's right. If rho is the hold on.
Yes.
Is that right? If there are row regions and all of
It's greater than, isn't it?
Yeah, it should be good.
I think let me just say this correctly. If the degree of every region is 3 at least,
Yeah.
and then multiplied by the number of regions,
It's still greater than.
then the sum of the degree of all the regions
It's greater than.
It's greater than.
is greater than or equal to 3 times the number of
Yeah,
regions.
3 is
Yup.
the minimum.
Yep. And this is 2 epsilon, so 2 epsilon is greater than or equal to 3 rho, and so rho indeed is less than or equal to 2/3 epsilon. Okay, good. That was the part we are. This is like total 100% review. We did these exact problems last week in this period. So good. The final thing says, use Euler's formula, Gossett calls it, but maybe people get mad about that. So I've been calling it Euler's characteristic formula to complete the proof of the proposition. Okay, so what do we know? Euler's characteristic formula says that the number of vertices, which I guess we're calling n in this case, plus the number of faces or regions minus the number of edges is 2. I guess this just like works out then, right?
Plug it in.
You just kind of like plug it in. So yeah, so what I have here is that rho is 2 plus n, or 2 minus n plus epsilon. What do I know about rho? It's less than or equal to 2/3 epsilon. So 2/3 epsilon, so that means 2 minus n plus epsilon is less than or equal to 2/3 epsilon. And then, does it just like work? It just works. Yep. Multiply through by 3, 6 minus 3n, and I can, whatever, I'll just keep going. Plus 3 epsilon is less than or equal to 2 epsilon, and that is exactly what we need, what we wanted. Epsilon is less than or equal to 3n minus 6. Good? Say good.
Good.
Okay, good. What this says, although I have no intuition for these particular numbers, although maybe you do, but what this says is that, look, if your graph is connected, planar, and simple, there can't be too many edges. Because the more edges you give me, the less chance it's planar. And so this expresses a relationship between the number of edges and the number of vertices. It says if you have a lot of vertices, then your edges have to be pretty small, otherwise it won't be planar. Does anyone have like a direct intuition about why those numbers are what they are? I don't. I just have this proof. Okay, good. Well, what we can now do is we can prove that K5 is planar. And this is how it's usually done because not planar. Not planar. Good. Graph theory teacher. What was our old proof that K5 is not planar? It was just like, come on, man, of course it's not planar. Because like, that's like a lot of points. It's like not even close to being planar.
Wait, it was just like try to make it planar. And, like,
It was just, our old proof was like try to make it planar and you can't. Yeah, in particular, what we said was, I think we deleted like 2 of these or something, right?
Oh.
And then we were like, alright, we were like, well, it probably, what? Deleted 3 of those. And then we said, okay, like how would you take it from here, so to speak? And the answer was, taking it from here, I need to connect like on these 2, so I could, you know, go around the back or whatever. And same, I need to connect
The ones on top.
these 2, so I can do that. But then how am I going to?
No, it's
What?
like start with
It's
like,
pretty much what we did.
wait, start with like K4.
Well, this is what I'm doing now. This is a proof. I'm not claiming this is a good proof. I'm claiming it's like, it's like a.
I can tell you a good proof right now that's just as concise and like exactly.
Okay, can I finish? Because I'm kind of done.
Sure.
I need to now connect these 2, and I sort of can't. Okay, and so that's like a, says Hayden, bad proof. Can I? What's a better one that's still sort of informal?
Start with K4.
Start with K4, which is planar.
And I draw the edges K4 so that's plain.
Let's see. What's the good way to do this?
Square.
The square and then one outside.
One diagonal and one outside.
Sure.
Now you have 4 regions.
I do have 4 regions.
Each region, right? Like this is like bounded by three vertices, right?
Yeah.
So no matter where you place the 5th point, 5th vertex rather, there will be one vertex that it can't connect.
Yeah. Okay. So good. So I have. So what Hayden's saying, just to rephrase, I have one more vertex, and like there's just nowhere for it to go, right? Because no matter where it goes, there'll be one vertex which is like, you know, sort of, yeah, outside or inside the region. Yeah, I guess why this is not considered to be a formal proof of this fact is that in order to actually show that K5 is not planar, I have to consider every possible planar embedding imaginable. And I don't know if this proof is like totally exhaustive. Maybe you could argue that it is. I don't know why I have to start with this particular configuration of K4 necessarily. So it's typically easier to just like, you know, cite this theorem. So anyway, this was number 2 from the homework. It said just like use this theorem, man. So let's talk about it. Why is K5 not planar? Well, suppose it is. Suppose K5 is planar. Well, K5 is certainly simple and connected. And so it must satisfy the theorem. But of course, there are 5 vertices in K5, and there are 10 edges. And yet by the theorem says that 10 has to be less than or equal to 3 times 5 minus 6, and then that's just like, it's just like not. So that proves that K5 is not planar. Good. Good the board. All right. So good. Should we do like one of these like Kuratowski's theorem problems? What did I assign? 1, 2, like 3. I assigned like 5 problems. Yeah.
3, 5, 6.
It's very pretty. Can I erase this? What is this supposed to be, by the way?
It's a big old cube in like nth dimensional space. Perfect.
Love it.
Which dimension?
It's like
I don't know.
a 5.
It's an 8.
Drawing.
Good.
How do
Beautiful.
you make it to 8? No, that's
Swung the camera around. Good. Let's do like one problem. What did I assign? 1, 2, like 3 something something?
2, 3, 5, 6, 7.
5, 6, 7. Let's do, what's the hardest one? 7?
I thought 3 was pretty.
3 was hard. Show that the Peterson graph, shout out to Rathi, contains a subgraph that is homeomorphic to K33 and so is non-planar. Oh yeah, this is kind of hard. So we have this theorem, Kuratowski's theorem. We did not prove it, but we talked it out. That well, let's just start. So what is the Peterson graph? And actually, okay, so let's do it. And then we also have some stars. And then each of these is connected to its adjacent one, and then there's just like a star formation. Okay, so that is the Peterson graph. All right, this particular embedding of the Peterson graph is obviously not planar, but that doesn't prove that the Peterson graph is non-planar, and it sounds like it would be really hard to do so. And so that's the power of Kuratowski's theorem, is that if I can show that this graph has a K5 or K33 like hiding in it somewhere, then it's not planar. All right, how do you do this? I don't remember. Oh, also it kind of told me use K33.
Yeah.
So you have to stare at this and you have to find a K33 somewhere in there. Note we have 10 vertices, and so 4 of them we're going to kind of ignore. Either because the subgraph is K33 and we're going to ignore it, or they're like a piece of K33. Alright, so who's got something? Alright.
Yeah.
This guy, whoa, is that like right?
Yeah. I did it with the click and drag app.
Okay, with a click and drag app. So
Very nice.
No, it was spot on.
so let's see. La, and then this you kept. Good? Yeah. So what he did effectively was to delete this vertex. He just killed entirely, which kills this edge, and this edge. And additionally, that's it? That's it? That is it, right? 1, 2, no, you killed another edge. You also killed this edge, and that's it. Okay, well, is that obviously K33? No.
No, because it's more vertices.
So explain.
Not K3, but it was like,
Homeomorphic to K33.
Yeah.
Oh, please elaborate.
I drew a picture. Like you can just redraw it as like obviously homeomorphic to K3.
Oh, I see. This entire problem is this page. Wait.
No, it's just the.
Oh, okay. Then he says, oh, I see. So I need all these like labels and stuff. So this is A, B, C, D, E, I, F, G, and J. Oh, gosh. So you have E. Actually, I can do this like a little bit better, maybe. So what he said, or I can just do this using the original thing. So he says E, F, and C are one color. All right, so let's color E, F, and C. This is like the alpha. And the beta set is A, B, I. So let's do that. A, B, I. And then you're saying that G and J are just along for the ride, basically. And D as well. So actually, that's pretty good. That's K33 right there, man. Every vertex, every red vertex is connected to every green vertex, treating like G as if it's just like not really there. Same with J, same with D, and yeah, done. We'll get to it. Good. Woo woo. Okay, good. Can we put a close on this topic of planar graphs, etc., etc.? Say yes.
Yeah.
Oh man, energy level very low. Good. All right, it's time to introduce like the last new big idea, the last new big non-polyhedra idea, and that is this thing you may have heard of it called the Four-Color Theorem. All right. So what I would like to talk about is map coloring.
Wasn't that fruit kind of
All right. Suppose you have a map. And let's like go historical about this. Suppose you have like kind of a map of like, you know, the United States. And you know, Florida's like over here, and here's like Georgia, and then this is like North Carolina, Maine's up here. This is supposed to be a joke. California, you know, Texas, etc. Okay, and so you have, all right, you have all the country split up, and then you might have some like weird stuff too, like what's the, you know, the state in the United States which borders the most other states?
Missouri.
I thought it was a tie between Kentucky and Missouri, maybe.
So it's like two.
I think Missouri is like 9 or something outrageous.
I think they're both 8.
They're both 8? Okay. Yeah.
Sure it's 7.
Good. It's 7? Someone look that up. I once, 10 years ago, had a period where I had 2 consecutive girlfriends who were from Missouri. And at one point, one of them accused me of being like an East Coast elitist and asked me to name all the states which border Missouri. I'm like, I'm an American, like I know all the states. And I started and it was a disaster. I got like half of them wrong. And she was just like, I've lost all respect for you.
Tennessee, Missouri.
What?
Tennessee and Missouri have 8.
Tennessee and Missouri have 8? You just consulted your brain map of the,
It was 8.
7? He said 8.
It says 8. It literally says 8 right here.
Good. Well, so yeah, what could happen is you could have like a Missouri type situation where there's then like it has a lot of states that border.
Map and it's 8. I'm looking at a map.
I believe in this.
All right, so good.
Google it, it's 7. So like.
No,
Good.
I just Google it says 8.
All right. Whoa, that's like weird that there are discrepancies over something as simple as like America. All right, good. So, does everyone agree that this problem is like understood now as like what?
It's really 7.
We haven't even started talking about color.
Wait.
I haven't even said anything yet. That's right. Thank you for pointing that out. All right. The question is, I now have a map of the United States. And here's what we want to do. We want to color this map. Whoa. How many colors do we need? Well, so you might think that this problem would have arisen naturally. Yeah, stop talking. I'm making a video over here. I would have maybe thought that you would maybe think that this problem would arise naturally in the field of map makers, but apparently just like not. Map makers are like, dude, we just do whatever. And but like, this is an interesting kind of math problem that sounds sort of like discrete math-ish. Like, how many colors do I need? Well, like, you can just start. Should we just all do this together?
Yeah.
Good. Everyone come up to the board. Here are 5 colors. Try to do it all together without screwing up. Go.
You
don't even need 5 colors.
You should try 4 colors.
Okay, try 4 colors.
Just try with like 2.
Okay, but like, I want like one person to have each color. That way, like, we can do this whole thing in like a minute. People at home, let's zoom in. Let's see if they screwed up because, like, you know. Good. Go faster. Wow. Okay. Nice.
That's also.
Can you like fill in the whole shape? Wait, Fu-Chang, you're being.
Okay.
Okay.
Fill in the whole.
All right. This is riveting. I should have made a smaller map. Go faster. Go faster. Oh, Fu-Chang screwed up.
There's a border.
Because oh yeah, I should probably have mentioned. I should probably have mentioned the actual problem, which is, of course, if you are going to color a map, then you want to do it in such a way that no 2 bordering regions have the same color. Was that like kind of clear in the setup?
I think it was clear. They just had one person do the whole map.
Okay, good. All right, should we stop now? I feel like we've proven our point.
No way.
No. I mean, that's
I want to actually color it.
This is,
what?
I don't know what we're doing.
You don't know what we're doing?
No, I know what we're doing. I don't know why we're doing this.
We are. Oh boy.
It's just an interactive class experience.
It's an interactive class experience, yeah. Notice this, like, kind of people at home. Notice this kind of circle in the middle is kind of interesting, right? But, like, actually not, because, yeah, you get to reuse a color like that. No, what?
Oh!
This is why. No.
I think you can make this black. Oh, you made this red. Never mind.
Yeah, you can make this one.
Okay, good.
Wait, that's this
Good.
one.
That's
They're not
fine, yeah.
ordering.
How many colors are we using? 4? Yeah. Alright, so jumping to the end a little bit, it appears that you can get by with 4 colors. But there are like many asterisks to this
I
fact.
think this can be blue and that can be red because these
No,
are only, no, these are only by a point, so you can.
Okay, you guys almost done?
Almost,
Yeah,
yeah.
this one.
And that's only by a point there, so just like green by.
Yeah.
Woo! Alright, round of applause.
Teamwork.
Team, that was the worst applause. Only the people who were being applauded for applauded. Alright, good. Yeah, so they, I handed them 5 markers, but they boldly said, nah, I can do this in 4. And in fact, there is a theorem called the Four-Color Theorem, which says, maybe you've heard of it, it's kind of like a famous thing, that you can color any map with just 4 colors. Such that no 2 regions sharing a border have the same color. Alright, and there's like many, hold on, there's, I'm on the Wikipedia page now, but there are many little things that you need to mention. 1, a state must be contiguous. So no like, you know, like Michigan type situation. That really belongs to, who did Michigan steal that from? Canada?
Wisconsin, what?
Wisconsin? Is it Wisconsin?
Wait, you historically or?
Upper Peninsula, yeah, I meant historically.
Oh, I don't know.
Good. I read something about this recently, but I forgot. So yeah, if you have like our previous fight from 3 weeks ago, Kaliningrad, a non-contiguous piece of Russia, that would require by conventional coloring 2 separate, or you'd want to color that those 2 non-contiguous regions the same color, just for like clarity. But if you have many non-contiguous regions that need to be the same color, then like it doesn't work. Follow? Okay, so we're assuming that the regions are all contiguous. Also, we have to point out that points which like are at the border of like many different regions do not count as being in, like, notice how these people colored this region black and this region black. Like, that's okay, right? Because these 2 regions share only like a single like point in common, so they can be the same color. Otherwise, if you insisted that even regions that share only a point, why is that a problem? Yeah, then you could just have an arbitrary many number by like just keep dividing this. If every single one of these regions needs to be a different color, then there's no upper bound in the coloring. Follow? Yeah. Okay, good. All right, so apparently this problem emerged somewhere in the 19th century. Some English people were just speculating about this, and one of them had like a brother or something who was taking a class with De Morgan, Augustus De Morgan of De Morgan's Laws, and he didn't know anyone had ever heard of this problem before. He sent him a letter, blah blah blah, things happened, everyone was like, oh, I don't know. They were pretty sure the idea was that they could only do it in 4. And actually, wait, this part's kind of cool. The history of this, I can't remember whether this is on the Wikipedia page or not, is, no, yeah, here it is. He says, De Morgan says, he has reduced it to, he says, okay, we never need, this is a quote, this is a direct quote from De Morgan's notebooks from Wikipedia. He says, all right, we never need 4 colors unless there are 4 counties, each of which has boundary lines in common with each of the other 3. Wait, what? That's a good question. What does he say?
Wait, just
There's okay. Even a neighborhood.
you only need 4 colors if like you have a situation where one thing is bordering the other 3. It's like obviously true.
Wait, what? Stop.
No, he says,
You don't need 4 colors.
Wait,
Do you think the other
okay, here's what he says. He says that there is some kind of principle at work. The principle is 4 areas cannot each have a common boundary with all the other 3.
Wait, that's...
Unless one isn't fully enclosed within the others.
Oh, yeah.
So what De Morgan is saying is that this is possible it is possible for 4 regions to all border each other. Okay?
Yeah.
But only, he says, the only way for 4 regions to all border each other, I think if I'm interpreting this correctly, is this way,
Yeah, with one in the middle.
with one in the middle.
What do they say?
I think that's what he's saying. But there's no other way for 4 regions to all border each other.
Well, like there is like, oh wait, no, I'm just gonna do it.
What did you just draw?
Like you close, like you make the outside the other way.
4 areas cannot each have common boundary with all the other 3 without enclosure. Yeah, without enclosure. Yeah. Yeah. So okay, yeah, maybe that's worth mentioning. You have also, this is like I'm just like winging this. This is a pretty bad video. So yeah, Dilham says the other way you could do it is if you had like a zone, and then like a zone, which is allowed. And then in which case you could color all this one color, and then you could, for each of these, you could do a little thing. All right, so this can happen, but otherwise, without enclosure, says De Morgan, it's impossible for 4 regions to all border each other. And he says it doesn't seem that this fact can be like proven. It seems so basic and fundamental that he says it is not capable of demonstration upon anything more evident. So he's like, he just throws up his hands and he's just like, look, this is just got to be an axiom, man. This is 19th century. It's a long time ago. He says I can't prove this. All right, fast forward to graph to like a taking more of a kind of a discrete approach. This is a kind of sounds like a hard problem in that we have to speculate upon all conceivable ways of making a map. So that's like, there's just like clearly just like an infinite number of different possible regions. So how can I ever get some sort of like clarity with this? Well, it turns out that even though there are an infinite number of different possible curves that can be in an infinite number of different possible arrangements for arbitrarily large maps and arbitrary numbers of regions and everything, really all that matters is whether 2 regions border each other. And so what we have done, can I get the purple, wherever it is still in purple? What we can do to turn this into a discrete problem is recognize that really all that matters is whether 2 regions border each other or not. So pick a point in every region, and so let that point represent the region, and then connect 2 points if their regions share a border. And now, la la, and la la, and la la, and la la. Right, and so now I can abstract away from the particular shape of the particular regions of the graph, and I can just say, okay, dude, this is really now just a problem of, here is a graph, and I can color the regions using just 4 colors,